this is the special offer what you are seeing. It popped up automatically. Okay, so make sure the pop-up are enabled. Maybe it is a pop-up only. So I would have to choose this offer. Okay, for this particular. However, they may be doing internally, but for your registered email address for the certain event, during the event, whatever URL they provide, once you go there, they let you, land onto this page, and this pop-up, this what do you say, pop-up, comes up, and you select the credit. Okay, select the offer. Basically, it's nothing but $500 credit, right? And then you complete the account process. So here, the cloud account name would be the Tennessee name. You may choose anything or whatever by default gets created. Go with it. And then let me just do this. I did not want to do this, but let's just do so that you guys learn this part. You are advised to create, attend some or other events from Oracle, whichever interests you, and also take benefit of such credit for exploring cloud, right? Let's say I would say Jigar Pandya and some name, let's say live one, okay. Then I will say home, and then I would say continue, okay. Okay, then it asks for address line 1, etc. So address line 1, let's say 18. Okay, I'll just say Anand for now. Okay, and these are all, everything else is optional. What was it? State, right? And then pin code 388315. Okay, so that's about it. I mean, you then just say. Okay, I'm not certain. See, this is the second account. I don't want to really create this. They'll definitely give you me. I wanted to just attend the event with two different tracks. That's why I created. I was okay. Is the contact number optional? I don't know. Is it optional or not? Because I have not read this particular. Definitely get me the credit what I'm expecting to do. Okay. Um, but just now I don't want to do this. Okay. Because I already have another account. I just don't know. So students, please see if you can grab credits. How am I using it? Right now for demonstrating to you all the remote procedure call? What I have done, I have instances, right? You show that you basically you create the instance. They will let you let's create one more here if you just want to check that, because we are going to need this. So all these things. I think compartment right? Then the image you can choose. Then you download this private key, because when you will want to connect to it, you will need that private key, and then you say create. So this will actually create a Linux machine of Linux 7.8 whatever Oracle version. Okay, it will take a minute or two. It's provisioning right now. Oh, okay. So see, I did not finish that Oracle credit part. I did not want to do that. But then, if you may have, BDS service or etc., which all things are free, I am not certain. But instances are free. I mean, Linux instances, basic Linux instances are free. Okay. Just now I created this another instance, and very soon I will be demonstrating you RPC, remote procedure call. What is expected from RPC? You might know from your theory from 5th semester. So can someone tell me RPC was demonstrated to you in your fifth sem remote procedure call? Did you do like multi-computer remote procedure call or no? Students, in your operating system subject, did you do remote procedure call development or demonstration or anything on those lines? So no, fine. So the efforts which I'm lying, which I'm laying, it will be a simple demo, but I already did in the past. Just because we don't have two computers in a place right now, I will have to demonstrate to you over cloud. Anyways, that is not complete yet. So I will not demonstrate today, but Monday during the lab, I'm expecting to demonstrate RPC as well as message passing interface, those demos. Okay, fine. Anyways, so I believe you seen that pop up, right, which came up for 500 SCD and all. So it was visible at the time because I see some chat saying screen not visible. Okay, okay. So guys, refer my email, the URL I provided, register 2 events on Oracle, and maybe learn also as well as grab credits also for exploring different things. Okay, fine. Okay, so let's move on for today. I will present entire screen just so that I don't want to have blind presentation. Okay, what is due for today? Let's see. All right, so you're seeing my screen, right? Last week, maybe Friday, we discussed about something called McQuarrie's algorithm, right? So we are continuing theory now. So we talked about McQuarrie's algorithm. So those who are not present at that time know that we are discussing distributed mutual exclusion. I repeat, distributed mutual, my goodness, mutual exclusion. We are discussing that. And there are various algorithms. One will be, timestamp based. In general, you can say token based or non-token based. So non-token based are primarily, timestamp based. They will be internally using timestamp uh, as well as the logical time clock. So Lampert's algorithm was the one which we described, and we already had algorithm also, sorry, example also. So this example, what we have learned, it was the Lampert's distributed mutual exclusion. Now the next we talked about token-based algorithm, and one of them is the McQuarrie's. Fine. Uh, okay. I'm sorry, I just say token based, but actually primarily we are talking about quorum based, QUROM, quorum based. Okay, and we say there will be mediator, right? One of the site which will be working as a mediator between any two other site, any two regions which you can say quorum. Okay. This R is actually request set, which is nothing but your quorum. Let me repeat. Just give me a moment. I need to drink water. Okay. Sorry about this. All right. Okay. So we are talking quorum-based distributed mutual exclusion algorithms. McQuarrie's is one of the example. It let you create quorums of sites first. What do you mean by quorum? Is group of sites. You can also say it as a request set. Now, what will be the specific about this algorithm? there will be at least one site common between any two quorum. Okay, so let's just see that example now, and that particular common site will actually help or act as a mediator. It will only give acknowledgement like a reply or a go message to either of the one, and hence this particular algorithm will confirm that only one person out of every quorum, first thing first, only one quorum will be in the mutual exclusion, I mean in the critical section, and out of that quorum only one person will be in the critical section. So it confirms that only one site will be in its critical section. So this particular scientist, he found that there is a relationship between the number of sites and the size of the quorum. I mean, quorum means group of sites. So what should be the size of that group? How many sites should be there in that group? So somehow Macqua found out a relationship, and he says if you have n number of sites, then the size of a quorum, I mean the number of sites participating into a quorum will be root n. So with that, the examples are, for example, you have three sites, which is nothing but site number 1, site number 2, and site number 3, for example. So if you have three sites, then the quorum size will come up to be root 3, which is the upper boundary, say 2, and hence you will have to create regions, of size 2. So 1, 2, 1, 3, and this is very much like permutation combinations. Okay, it is very much like permutation combination. You can think of writing a C program to generate the quorums, first thing first. Okay, so let's say 1, 2, 3, 1, then comma 2, comma 3 is number of sites. You may also say S1, S2, S3. Let's say S1, S2, S3. So what will I do? I'll say S1 and S2 in one quorum. In another quorum, this number don't go with this number. It's just the name. Okay, R1, this R1 or R2 or R3, they are just names. It can be any name. This can be like region X, region Y, and region Z, or request set, whatever the name might be, or quorum 1, quorum 2, quorum 3. These names can be anything. Important thing is who are the participants. So site 1 and site 2 are participants of quorum 1. Then site 1 and site 3 are participants of quorum 2. Site 2 and site 3 are participants of quorum 3. So if you know NPR, NCR, etc., right? So you will understand 1, 2, 3. That means 1, 2, then 1, 3, and then lastly 2, 3. So that way you can create these quorums, fine, of size 2. So if you are good at maths and if you are preparing for GATE, you will need to learn and apply those things here. For example, you have total number of 7 sites, and root 7 is hopefully 3. Fine, root 9 is 3, so root 7 is we expect to be 3, right? So how many total number of quorums will be there? Which is this mathematical formula? I mean, is it 7P3 or 7C3? I'm very bad at maths now. It's been years I actually tried maths. But you see, at least it is 1, 2, 3, 4, 5, 6, 7 total. I repeat this way: 1, 2, 3 vertically, 4, 5, and 6, 7. These are nothing but your quorums. And you see how they are created, very much like your permutation combination way they are created. Okay, and importantly, if you will see the intersection part, you take any quorum, let's say R1, and go check with every else. So 1, R1 and R4, is there a common guy? Yes. R1 and R7, is there a common guy? Yes, right? And that is what we have seen for R1. Same way, can we check for R2? R2 and R1, is there a common guy? R2 and R3, is there a common guy? Yeah. R2 and R4, is there a common guy? right? R2 and R5, is there a common guy? So you understood what is the purpose? What is the logic behind how to create quorums? Did you understand? That's very much mathematical, okay? You have to create quorum such a way that every site is member of, there is one common member from every quorum to each other. Okay? I hope that makes sense. May I move on with that? Please type it into the chat window. Did you understand how to create quorums? What was the concept behind quorum? It's on the mathematical requirements of the algorithm, MACWAS. Students, given n, maybe you want piece of paper, or maybe you write a program to do the same thing, C program or Python or whichever. Did you understand the logic? What's behind the scene? It's very much like some other permutation combination, but you still have to be good at maths to create this. Will there be another result of set? So let's say these are 7 sets here. Can I have some different types of 7 sets? So that all actually falls as per the mathematical understanding of yours. Okay. So you have to improvise your and strengthen your math to work with algorithms. That's for sure. Anybody good at maths? Or can you give me any input on that? Are like me only, huh? Okay. All right. Fine. So know that if you want to be, a data scientist, or if you want to have a high-profile career, particularly with algorithms and architecting, big things, you have to sharpen your maths skills, and you still have time. Keep sharpening your mathematical skills. Maybe via preparing for GATE exam and then appearing likewise like for. Okay, but then you got to definitely have mathematical skills. Smoothly understand and recreate new algorithms. Okay, so this R1 up to R7 are nothing but quorums, and they have members, okay, which are the actual sites. And as per the logic, there is at least one common member amongst every pair of quorums. And how it helps, that common member will not give go, like green signal, to both the groups. It will only go green equal to only one group, and hence at a time there will be only one quorum will have a green signal, and that's why. And of course, within it will have requested the acknowledgement. So let me repeat the algorithm. What was the algorithm? In the previous Lamport's algorithm, any site wants to enter into critical section, it will seek acknowledgement from all the sites. So let's say there are 7 sites. Then in the previous Lamport's algorithm, site number 5, for example, will seek acknowledgement from all the remaining sites. Versus in the current MACWAS algorithm, we have actually distributed the 7 sites into multiple quorums like this. Okay, and now let's say site number 2 wants to enter into critical section, so it will not send the replies. It will not send the request message to everyone. It will only send request message to 1, 2, and 3. Now let's see how it works. So what is the scenario right now? Site number 2 from quorum number 1 wants to enter into critical section. It sends request message to site 1 and request message to site 3. Now let's see. So this site number 1 will have to acknowledge to site number 2, as well as site number 3 will have to acknowledge to site number 2. And if 1 and 3 both acknowledges to 2, we'll check other conditions, but at least that will let site number 2 move on to use critical section, for example. Now let's see, if site 1 is acknowledging to site number 2, that means that will not acknowledge to any other sites, okay, yes or no, in any other quorum. So that means site number 1, let me repeat, site 1 wants to acknowledge to site number 2, saying go ahead. In that case, let's say it did it. Let's say site 1 say, site 2, you go ahead and use critical section from my side. I'm giving the go signal. At that time, then site 1 will not give go signal to any of others like 4 or 5 or 6 or 7 or up to that. If now 4 and 5 comes up, any of them, or 6 and 7 comes up, any of them, they will not enter because they will not have go from site number 1. Let's talk about site 3. Let's say site 3 also gave go signal to site number 2. That means site 4 and 7 as well as to 5 and 6. So if you really understand who will not go inside the critical section, let's say 4 will not go, 5 will not go, 6 will not go, 7 will not go, they are already there, 5 will not go, 6 will not go, right? So basically, and 1 knows that it has given permission to 2, that's why 1 will not go, and 3 knows that it has given permission to 2, so it will not go. That means no other site will enter into the critical section in this particular scenario. Did it make some sense, at least from this example? We can read the algorithm, but this is basics about it, how it works, okay? And yeah, that's about it. I mean, that is what McQuarrie's algorithm is. It is based on quorum, and the logic is this. The how it will move. We can still check few more steps here. Requesting the critical section. A site SI request access to CS by sending request message to all sites in its request sets. And this request sets is nothing but your quorum, your own quorum. Okay. And then when a site SJ, I mean, when let's say in this example what we talked, when 2 requests to 1 and 3, what 1 and 3 will do? So that is site SJ. Either site number 1 or site number 3, you without loss of generality, you think them as site J. Let's say site J receives request from site 1, site whatever 2, right? It sends a reply message to that particular site, provided it hasn't sent a reply message to any other site. Okay, since last it receives of last release message. I mean, there is nobody in the critical section and it has not sent any reply to anybody else. So it will now send reply to let's say 2. So that way 1 and 3 will send reply to 2 saying go ahead. And if that happens, they will not send reply to any other if there is any other request coming out from 6, 7 or 4, 5 or 4, 7, etc. And that will actually confirm so when will you execute critical section? Any site which has received a reply message from every site in its quorum, it will go ahead and execute the section. So there are no more conditions here, only one simple condition. You go ahead to critical section if you have acknowledgement from your peers, from your quorum, and they will only give acknowledgement to 1 at a time, right? So that will confirm. After the execution of CS is over, of course, now we are talking about release. So site SI sends a release message to every site in RI, and actually there is something called, there will be a queue. Yeah, there will be a queue, okay? Because in the message passing system, I mentioned to you, you cannot just ignore messages. It depends how the design is, but mostly there is some, like, there are also waiting queue kind of stuff. So here, for example, when site 1 gave acknowledgement to site 2, at that time, after a while, let's say 7 requested to 1 saying I need to go and use critical section. So what will site 1 have to do? It will have to queue number 7, so that whenever it receives the release message from site 2, it will then be able to, go and say, give green signal to site number 7 likewise. So I believe you understand what I'm talking. Every quorum, every sites actually will be also maintaining something called waiting queue. Okay. So when a site Sj receives a release message from site Si, it sends a reply message to the next site waiting in the queue and deletes that entry from the queue. If the queue is empty, then site updates its state to reflect that it has not sent out any reply message since the receipt of last release message. And this is actually the next step. If nobody is there in the queue, that site might send, so they have not clarified how exactly it will do, but they say if there is nobody in the queue, the site updates its states. So its states means it will have its own data structure to reflect that I am available, I have not sent reply message to anybody, and likewise. Okay, so there are actually, analysis on that, like performance, etc. And this works. This is the correctness proof, and again is proved by contradiction. So suppose two sites concurrently executes the critical section. Suppose, and if that is happening, what will happen? If both are executing critical section, what might have happened? Both would have received a reply message from all their quorum members. Yes or no? But then we know from any quorum, like between two quorum, there has to be a common site, right? Now, is it possible? This site, common site, which is SK, as both of them are executing CS, SI as well as SJ, which are there in different quorum, and as per the algorithm, they will execute critical section only if they request, only if they have received acknowledgement from all. That means SK has given acknowledgement to SI as well as SJ both, right? And we know that there is a condition that any site can give acknowledgement to only one at a time, and this is what is getting contradicting, right? Because as per the rule, site can send acknowledgement to only one, but this situation says SI as well as SJ both has acknowledgement from SK, and that's not possible. That means it is a contradiction here, and that confirms that McQuarrie's algorithm achieves mutual exclusion. So that's theoretical proof of McQuarrie's algorithm to achieve distributed mutual exclusion. Now, fine. So if you may observe the complete algorithm, you may end up in finding that there is a problem with this algorithm, and that's it is a deadlock prone algorithm. There can be deadlock also. Okay, I will not go in depth of this, but maybe we have a diagram which might, yeah. So this was the example what we used to describe. So provided you have so many sites and quorums, etc., and provided certain steps have been happened, so what would happen? There will be a deadlock situation. If you want to observe and understand, I can still help you on that. Can someone try deciphering this image? It is basically conveying that there is a deadlock. Now, if you can decipher, otherwise I will definitely do that. Can someone decipher this image, which actually conveys that there is a deadlock? Fine. So let's understand. So we have all these sites which are nothing but this number 1, 2, 3. They are site number, computer number. Okay, and then what is it? So 11 sends some message to 12 at the same time. 11 also wants to send some message to somebody else, and they are called R message. We have to actually understand this. So the problem was with this image was this R and L, the terminology is not given. What do they mean by R? What do they mean by L? That is not given. Because you may think like R means request, but it can also mean reply. That's bottom line. So the terminology is not given. That's why it is not easy to decipher this. L, I mean, what you may think as L, maybe lock, something on those lines, right? But still, it's just a guess, right? So let's just see what happened. So site number 12, it says it is locked by site number 11. And site number 13 is also locked by site number 11. Okay, so fine. So imagine site 12, I'm trying to clarify, okay? I know it might be wrong. Let's just try to see. Imagine site number 12 requested a go from 11, and actually we have to also see the quorum. These are all the quorum given, okay? So they have not drawn any boundaries here, but you have to see like how many total number of sites are there? 12 or 13. So given that 13 sites are there, what will be the size of a quorum? Is it matching to the theory? Root 13, square root 13 means square root 16, right? 4 basically. So this is matching, and these are the quorums, right? Now 11, 12, and 13, they fall where? So 11 is falling in let's say quorum number 2, okay? Then 12 is falling in site quorum number 6. Likewise, like 4, you'll have to check, okay? It will definitely fall more than one quorums, okay? So the thing here, you will have to find out which quorum does it belong and why it is creating deadlock, okay? So for now, I'll leave this as an assignment. Know that I have deciphered this and explain to students. The only thing I would not want to do that right now, because that will not leave a chance of an example for you, okay? Because we don't have many examples, we have only whatever in this slide. So you try to decipher this and try to find out why it says that site number 11 is locked, okay? Okay, so basically it is conveying that it is deadlock happening, okay? If the algorithm is followed. That means nobody is going into and entering into the critical section. That's what has happened here. That's what deadlock means, okay? Fine. In next class, if you have not, okay, anyway, they have given the solution also. So anyways, they have given the solution also, right? So basically, there are multiple screens, right? If you will follow each of them, then you will understand that there are actually deadlock. And the solution for deadlock is also given, okay? And that is something called, okay, I have 2 slides, so I don't know which slide is which one. But then there is solution also, okay? Okay, let's see, you want to talk this, then the only problem was the terminology was not given. That's why it was a little difficult to get through. Okay, let's go slide by slide. Okay, fine. So locked by 11, and this is again sending, like the message is in the transit. This message is in the transit. Okay. Now this message is like in the transit. Okay. Now let's say this number, another site called 7, which has also requested something, and this message is in the transit. Okay. So I think you will be able to now somehow better understand. This is the previous slide, right? And the next is this. You may now understand a little bit better. See 11, 12, 13, and this arrow, which goes to 1. It looks like 11, 12, 13, and 1 are somewhere in this here. Which one? Which quorum has 11, 12, 13, and 1? Do you see anywhere? Yes. Right, Ria, correct. S11. So we are right now talking about this particular quorum, okay? S11. The member from S11. Okay, now again, see here, it should not say S, it should say quorum or something else, because S, confuses with site. So please don't confuse with the terminology. The author would have something, but they have not given the legends. Anyways, so S11 is nothing but our quorum 11, okay? And 1, 11, 12, and 13, they are the members. So 1, 11, 12 and 13, they are the members. 11th site wants to access critical section. It started sending the request messages to all the 3 remaining. And the third one is in transit right now. And this L is actually the acknowledgement, okay? So let's say 11 requested to 12 and 12 said, okay, go ahead. 11 requested to 13 and then 13 said, go ahead. 11 is right now requesting to 1. That's the scenario. The next, in the parallel, maybe some other things are also going on, which is with this. Site number 7 requested 10. Site number 7 also requested 2. So which quorum it might be? And the next, site number 7 is about to request to 13. That message is in transit, for example. Which quorum is it? Site number 7, then 10, 2, and 13. Yes? 2, 7, 10, 13. So the quorum number is S7. Yeah? So please note that down. The quorum number is S7. Right? So there are 2 quorum which we are talking about in this example. And site 11 as well as site 7, both of them are requesting the critical section. Now what will happen next? Let's see this thing. Okay, what happened here? Something else increased, right? What was, so first we saw this, site 11, we saw site 7, and then, now what is it? Who is requesting? Site number 10, huh? Yes or no? So site number 10 requested to 7. Okay. And site number, fine. Site number 10 request, oh no. So let's see what happened further. So this is nothing changed. Site number 7, it requested to site number 2 and it has got, acknowledgement. It also requested to 10, it has got acknowledgement, right? And the request is not reached to 11, that is fine. And then site number 8 is requesting, see? Yes or no? Site number 8 is requesting. Now, what is happening here? Site number 8 is requesting to 9, 10 and 1. So where is 9, 10 and 1? I mean 8, 9, 10, 1. It is little, you will have to sit back. It was easy to, teach this on slide as well as with, blackboard and all. What we are talking right now, site number 8, 9, 10 and 1. 8, 9, 10 and 1. There is another quorum. Which is that? Do we have that? We should have it. S8 as per the 1, 8, 9 and 10. Fine. So now we have 3 quorums, what we know as per the diagram. So let me just, so Ria already mentioned S8. Fine. So what is happening then? I'll tell you what is the purpose of app, okay? I'll tell you what is it. It is actually deadlock handling part. We'll talk about it. So first thing we have to understand where is deadlock. I mean where deadlock has happened. So see this site 1 has sent acknowledgement to site 8, right? As per this arrow. So who is waiting? That means site 11 is waiting, yes or no? So waiting, confirm, site 11 is waiting yet? Students, can you confirm that site 11 is waiting? Have you understood that part? Number 1, give acknowledgement to site number 11, one person, right? So 11 is waiting, okay? Fine, it is waiting. Let's see who else is waiting. I got it. Now, can someone tell me where is deadlock? what is this F? So we know site 11 is waiting because the acknowledgement is given to 8. How about site 7? Can it go? Site 7 is waiting for 13. Yes or no? Right, correct. Maliha, you are right. Site number, who is interested? I mean, is 10 interested? No, right? 10 is not interested. Is 9 interested? No. Interested, you have to use CS. Who else is interested? 8 is interested? Yes. 8 has sent request. That means it is interested. Has he received from 9? And if it would receive from 10, it would be able to go. But then 10 has already given acknowledgement to 7. So just don't see this particular line, okay? Forget this F line. Forget this F line because it has a meaning, okay? I'll tell you what it is. Forget this F line. Know that if it is not there, what do you understand? So we understand that site, you may have to draw the resource diagram. You know, there will be a circle if you will draw. So 7 site is waiting for 13, right? Site 13, and then which actually is depending on 11, right? So can someone draw that diagram, or can someone make up that cycle diagram so that you confirm that it is actually deadlocked? Okay. From where to where we start? Actually, let's start from. Can 11 enter into the critical section? No, because 11 depends on 1, and 1 will be released only by 8. Can 8 enter into the critical section? 10. Can 8 enter into critical section? No, because 10, it depends on 10, and 10 is actually because it has given the go to 7. Can 7 enter into critical section? No, because it is waiting for 13, while it is there with 11. So I believe the cycle is clear. I may actually type it now. You may check the cycle. So 11 is not able to go ahead because it is waiting on 1, right? But 1 will be released only when 8 gets a go, right? But 8 will be released only when 10 gets, its release back. But then 10 will be clear when it will actually have, release from 7, and 7 is actually waiting on 13. 7 is actually waiting on 13. So there are two actually sets of things. One wants to go to critical section, and one will be waiting for release messages. So 11 is actually waiting for the acknowledgement from the 1, but 1 will be able to give acknowledgement only when 8 releases, its acknowledgement back. Okay, but 8 actually is waiting on 10 to get the acknowledgement, right? By the time 10 is waiting for 7 to say, okay, I am done, which is like a release message. Okay. So R here is actually request to reply and release. This R can mean any 3, and let's see if we have further diagrams. But deadlock, could you see the deadlock? 11 is not able to move forward because 8 has the acknowledgement from 1. 8 is not able to move forward because 7 has acknowledged from 10. 7 is not able to move forward because 13 has provided acknowledgement to 11, and that's the reason. Okay, 13 has already provided acknowledgement to 11, and 11 is actually waiting for acknowledgement from 1, while 1 has provided acknowledgement to 8. 8 is waiting on acknowledgement from 10, and it's actually a circle there. It's actually a circle, honestly, if you see clear. Okay, so the solution to that was actually something called a failed message. Okay, so first thing first, you have to understand the scenario. You have to know that there is a deadlock possibility with McQuarrie's algorithm, and that's because the messages send and receive mechanisms, right, and the network delays, etc. You might feel like, oh, site 11 requested first, so one should have given reply to site 11 initially, because we saw this diagram, right? We feel like, okay, site 11 started, so one should have sent reply to 11. Why would site 1 send reply to site 8? But then these are message passing, so messages might be delayed also based on the network and other traffic, etc. So that's when we expected that site 1 might have given the reply to 11, but that didn't happen. Site 1 actually gave reply to site 8. So this L actually is the acknowledgement, like lock part. Okay, I'm giving you go, like that. Okay, uh, and the solution to this deadlock is actually talking about something called a failed message. Okay, uh, so this is actually, they are talking deadlock handling now. Okay, so this when you see this failed message, what happens when site 8 requested request from 10 said I cannot give you, and that actually depends on the priority part. Okay, let me tell you that part now. When will fail message be given up? We will. So there is algorithm we are moving forward with deadlock handling solution. So McWa's original algorithm was prone to deadlock, but then it was improvised with another logic, something called F message, failed message, and it was then able to handle the deadlock. Let's see what is that. Okay, is it written somewhere in? I don't know if it is written in theory or not. Let me just see. If not, I will have to give you another slide, because there were two slides I was referring. Okay, handling deadlock. So this is the theoretical answer to handling deadlock. Let's just go through it. It will definitely make a sense. So there are two more types of messages introduced. One is called failed message, failed type of message, and another type of message called inquire. Okay, and as I mentioned, it now check the priority, and that priority is actually let's see. So when a request ts comma I from site si blocks at site sj, because sj has currently granted permission to site sk. This is what you understand, right? Site 18 for me. Then sj it sends a failed message. It says, I'm sorry, I cannot give you a go because I have given go to somebody else. So I repeat, site sj sends a failed message to si saying that I have given a go to sk, so I cannot give you a go. But when will it say failed message? If the si has a low priority. Okay, so basically, I repeat, sj has already given a permission to sk. At that time, si is requesting, and if si's priority is less than sk, that means sj learns that, okay, sk is having higher priority, so let it move on, and let me tell si to wait. Okay, so it basically sends the fail message to say that si, you requested, but your priority is lower than someone to whom I have already provided the acknowledgement. If it is on the other side, for example, site sj has given acknowledgement to sk already, and si is coming up. But if si's priority is higher than sk, at that time, sj feels like, oh, si's priority is higher than sk, so I actually have to do something to help si, and that is this. At this time, sj will send another message called inquire to sk. So what is the scenario? Site j, which is the mediator site, it already has sent acknowledgement like a go to sk, whose priority is smaller than si. For example, in that scenario, SJ sends inquire message to SK asking if you have not already started entering into the critical section. I repeat, SJ, which is a mediator, which has already given a go to SK, which has a lower priority, then SJ sends inquiry to SK saying, if you have already not entered into critical section and if you are waiting on somebody else, can you give my green signal back to me? I mean, can you return my reply back to me so that I can give that particular reply, or I can give you the go to the higher priority site, which is SI. So that is what will happen now. In the response to an inquire message from site J at site K will send another type of message called yield. And those who have traveled internationally, or maybe those who have studied, traveling document, like before getting to that driving license, they may know the yield. What does yield mean? So I tell you what does yield mean. If you are at T section or a four crossway and there are no traffic signal, something on those lines, or in general, let's say there is a zebra crossing and you are driving, so you should yield to pedestrian. I repeat, zebra crossing is there, you are driving, you should yield to pedestrian. That means you should stop, let the pedestrian pass by. That's the traffic rule in foreign countries. Okay, so that is what the meaning of yield. Yield means giving up. Okay, so we are right now talking about site SK. It has received the inquire message from J, and what will SK do? So SK will send yield message to SJ, provided SK has received a failed message from a site in its request set of its sent. So basically, site SK, if it is not in the critical section already, because of multiple reasons, one of them can be it already received a failed message from some other site. And when will you get a failed message? You will get failed message if your priority will be lower than somebody else. Yes or no? So if site K has actually not entered into the critical section because of the reason that it received a failed message from some other in its quorum, that means site K can release the acknowledgement back to site J. I mean, site K even wanted to enter, but then its own priority was lower than somebody else's priority, and hence it was in a waiting mode. So K will tell site J, I'm in the waiting mode because some higher priorities are taken care. So haven't given me a go signal. Okay, that is what it happens. So when site K yields, that means site J will then give the acknowledgement to the site I, which was having higher priority than site K. So from a site in its request set of its yield to any of those sites, but has not received a new grant from it. So this is actually a little longer algorithm, but hopefully you have understood. In response to the yield K message from site K, site J assumes as if it has been released by SK. It places the request of SK at appropriate location, which is like some other queue. But then it sends the grant type of message. So grant message is actually the another set of acknowledgement, like a second round of acknowledgement. Okay, it says grant J to the top request site in the queue, which might be SI, for example. So SI will learn that, oh, now I can go. Okay, so that way the deadlock is handled. So there are multiple level of communication. Okay, and I hope you understood this the purpose of failed message, purpose of inquire message, and purpose of yield message, and purpose of grant message. So other than request and reply, there are 4 more categories of messages: inquire, failed, yield, and grant introduced. And with that, MECWAS successfully handled the deadlock. So please go through this. It's actually showing you that scenario only. I told you that app signal, remember, failed. This app particular is the failed signal. So when it says failed, somewhere else down the line, you will also say inquire, I for inquire, right? I for inquire, C, right? right? And that's why the deadlock will be actually released or handled. So I mean, deadlock will be broken in a way. Okay. Uh, so inquire, right? This queue again, we'll have to think what is queue. Okay. Check on it. Fine. Okay, so we have completely understood the distributed mutual exclusion with two algorithms. One was the Lampert's distributed mutual algorithm, which was based on the timestamp, right? And another MAC which was based on quorum, right? We still have to understand something called token-based algorithm. And let me just tell you one line, then we'll move on. Token-based algorithms, more concept called sequence number that we will take up in the next class. We'll touch this particular one algorithm on token-based also, because I think token will interest you. Token as a data structure already interested you in the last class. Okay, so we'll talk about token-based algorithm in the next class, where we'll talk about something called sequence numbers. Okay, instead of timestamps. Fine. Over to you, next faculty. And students, this has been shared with you already as lecture 15 and 16, I believe. Okay, for the previous week's date, right? Maybe 10th and 11th. Please go through this PDF and learn more about it. Okay, and these are very much like the base or fundamentals of distributed systems. Okay. All right. Over to you, next faculty. Thank you.
Good afternoon, all. In today's laboratory, we'll discuss about the neural network. So quickly download the PPT of the neural network that I already shared in the lab folder, as well as open that Python file, and we'll similar to the last lab uh, where we have developed the code together. We'll follow the same approach for this lab as well as for the other labs. Code and open that Python code with the Colab. Okay, so for this laboratory purpose, we are introducing this neural network. I know you have the basic idea of that neural network, and at certain aspect, the Bridges sir has already discussed about the neural network, right? But the depth is remaining. So in today's session, what I will try to do, I will try to cover the not the full depth, not mathematical depth, but overall procedure of neural network, how exactly we have connection of neuron and how actually we can form the neural network in the program, right? So for that purpose, whichever uh, input are needed, that I'm supposed to provide for the laboratory, right? In lateral, maybe in our next lecture itself, we will discuss the neural network in depth with all its mathematical detail and the back propagation itself in depth, right? And we'll also see the free feed forward network along with the back propagation. And but that would be the next lecture. Right now, just the basic fundamental, how exactly neural network work, and that's it. And then we'll switch to the program where we'll discuss the one application with the help of neural network. Anju, this slide is just for the laboratory purpose. For the lecture, I will have another slide and which have very more depth compared to the current slides. Fine. And this is for today's lab and this agenda of today's lab. And in the next laboratory, that is on Saturday, if in tomorrow's session SVM is covered, all the concept of SVM is covered. I hope the one lecture is over and we have one more lecture of the SVM. So if it is covered, then we'll have program of SVM in Saturday's lab. Otherwise, we'll try advanced model, that is CNN, which is a deep learning model to process with the images. Otherwise, the deep learning model for the image processing, that is CNN, that we'll discuss in the next lab. Fine. But for that model also, if you want to learn about the CNN, this neural network is very important. So anyhow, we have to learn this neural network in lecture as well as in the laboratory. Fine. So in a neural network, there are mainly three kind of layers, right? So if you just consider this initial diagram or the initial figure where we have input layer, all these red neurons are actually input neurons. Next, we have n number of hidden layers. Right? It is not necessary that always you have to choose 1, 2, 3 or n number. What could be that number? It actually just in trial and error. You can say just in hyperparameter that you need to identify for the number of hidden layers. Right? And finally, we have output layer, which will produce the output or which will generate the output. Right? So whenever we discuss the architecture, so this is the basic fundamental, and majorly all the neurons are connected to all other neurons at the next layer with some weights. Right? So if you just focus on this first, is my pointer visible? Okay, so if you just focus on this first red neuron, and if you see the connection, so this red neuron is connected with all four neurons, that is all four blue neurons of the hidden layers, and so on for the others. Right, so sometimes we can also drop the connection. So there is one concept referred as the dropouts, but we'll not discuss about the dropout right now. We'll just focus on the fully connected network, where the meaning of fully connected is particular neuron is connected with all the neurons of next level or next layer. Right, so that is the meaning of fully connected layer. Right, and in general, we'll refer this architecture as ANN, which is referred as artificial neural network. Fine. So I have inherited these slides from some good material as well as from this N2NG course to discuss the basic fundamentals or basic concepts. Right. So input unit connected with hidden unit. Let's assume the simplest possible diagram where we have 4 neurons in input as well as 4 neurons in hidden as well as 4 neurons in the output layer. right? And all are connected with some weight to the all other units, or you can say all other neurons of next layer, right? So this is a fully connected architecture, right? And it is also referred as a feed forward network. So we are feeding, or you can say we are giving this particular data to the next layer, or you can say to the forward layer, right? So you know all these basic concepts, so I'm not going in depth of that, but we are interested to know this working. So at every neuron, and I hope in from the last lecture of Brijesh sir, you might clear with neuron, and specifically this particular perceptron, and you can say perceptron learning algorithm, and let's say this neural network. So what exactly is the difference, right? So now consider this x as an input. So this x0, that is our bias input, x1, x2, x3 are, let's say, three input we have, and this theta 0, theta 1 up to theta 3 are some weights via which will connect to the next layer. And assume that the next layer just have single neuron, right? For a simplicity, let's assume that the next layer have the single neuron. So at that particular layer will have the summation, or you can say the sigma. So two process will apply. One is the summation, or you can say the sigma, and the second thing that we are going to apply is the activation of that layer. And so keep this in your mind. At every layer except input, whenever you consider a particular neuron, will have two process. The first process is it collects the input, or you can say from whichever connection or whichever input it have, it collect that input and sum it together. And the second step is on that sum, or you can say on the result of that sum, it will decide whether it should forward that information to the next layer or not. So at every layer, that is at all hidden layer, we'll repeat this process. Or whenever I say all hidden layer means all neurons at all hidden layers. Right? So it follows these two steps. One is a collection, and another one is the activation. The activation means it will decide whether should I forward it to the next layer or not. Fine. So let's keep this information in mind. Fine. And whenever we say this summation, so what exactly it means? The summation is not just x0, x1, x2, x3, but that is the summation with respect to the weight. So that is x0 theta 0 plus x1 theta 1 plus x2 theta 2 and plus x3 theta 3. Right? So whatever is the result, that will be the summation. So that is the first part, or you can say first process done by a particular neuron. The second part can be second part is an activation. Fine. So over here for this diagram, the activation is the sigmoid function, or you can say logistic function. And so we are very well aware about the formula of logistic function, which is 1 upon 1 plus e raised to minus theta x. Right? So whatever is the result, that is this g of z, that will decide the input to the next layer. Right? And the same process will be followed by all the layers. So are we clear with the forward pass? This is referred as a forward pass. Means we are passing the information from the input towards the output. Friends, actually there are two paths. One is a forward pass, another one is a backward pass. Right, where the back propagation comes into the picture. While for this forward part, there are no back propagation or there are no such thing, right? So we'll just forwarding the information based on some computation or some calculation to the next layer. So it will take that information and forward it to the next layer. So this is the simplest, you can say, explanation of this neural network architecture. Right. So as I have discussed, we'll repeat this process at each and every layer. So assume that we have one input, one hidden, and one output. There are three layers. Right. So input is x0 up to the x3. Hidden layer, that is a0, a1, a2, a3. Right. And as it is layer 2, the layer number is indicated by this bracket. in a superscript, right? So at the layer 2, we have A0, A1, A2, and A3, right? So assume that uh, your activation is 10h function. So can you tell me what will be the formula of A2? You're assuming that the activation is 10h, right? So what will be the formula of this A2? So can I say that that would be capital X, capital theta, and whatever is that dot product will give it to the activation, that is 10h, and whatever is the result of that 10h, that will be the result of this A2. Fine, agree? Okay, good. And what will be the dimension of weight matrix which is in between layer 1 and layer 2? Dimension of weight matrix means how many theta values we need between this layer 1 and layer 2. So for this example, what will be the number for this example? Actually, number of inputs are 3, that is x1, x2, x3. This x0 itself is a bias. So can I say that the dimension of weight matrix which is in between layer 1 and layer 2 is 4? Malia says 12. See, whenever we say theta, let's assume that we are saying that theta 1, or you can say the weight 1. So what do you mean by weight 1? Is it the weight between x1 a1, or it's a weight between x1 a2, or it's a weight between x1 a3? Yes, it's 12 is correct answer, 4 into t, but let me justify that why it's 12, right? So once again, let me repeat the question. Whenever I say W1, or you can say theta 1, so what do you mean by that theta 1, the weight 1? Is it the weight between x1 a1 or x1 a2 or x1 a3? Okay, so I guess it looks confusing. So right now, let's just keep this thing in your mind. The final answer is 12. In the upcoming slide, we have that number, specifically the theta 1, theta 2, theta 3, everything is mentioned, right? So we'll better discuss that at that particular slide. Fine, and as I have discussed that this feed forward process, or you can say the forward pass, simply what we'll do, we'll have the computation and then lateral followed by the activation layer. Right, and that activation, the use of activation is generally to give the non-linearity to the given output, right? And for that we have various choice, and in today's laboratory itself we'll try to explore 2 or 3 choice, right? And one very popular choice which is referred as the ReLU, ReLU, right? So we'll explore that ReLU function also. Fine. Okay, so now focus on this slide. This slide is very much important. So assume this simplest diagram where we have three input, that is x1, x2, x3. Okay, three layers are there, right? Input, which is having three neurons, x1, x2, x3. Hidden unit, or you can say the hidden layer, where we have a1, a2, a3 of 2. Right? And this one is the last layer, that is the output layer, which is once again a1 of layer, or you can say output 3. Fine. So now over here the calculation of individual entry is given. So I hope from this you may able to justify why these dimensions are there, right? So for the previous figure, why Malia has mentioned that it's 12, right? And similarly for the next layer, why it is 1 cross 4. Fine. So we'll come to that. Let's just see this particular equation. A1 G. What do you mean by G? If you can recall last to last slide, what was the meaning of this G? Sigmoid, or in general activation. Right? It can be any activation, maybe sigmoid, maybe relu, maybe 10H, or so on. Right? So we have many different possibilities for G, but it kind of activation, any activation, right? So we'll apply activation on some equation. Fine. So now forget about this G. Let's see what's inside. So X0, which is, you can say, the bias at the input layer, which is multiplied with theta of 1, 0. Right now you can just ignore this superscript. This superscript just indicates 1. That means we are considering the layer 1. Fine. So theta value at layer 1. Lateral, whenever we see the theta value at the layer 2, which will indicate by theta 2. And so right now you can just ignore this superscript to make this equation bit easy. So x0, which is multiplied by theta of 1, 0, which means this last 0 indicate the previous layer and this 1 indicate the current layer, that is for the A1. Fine. So this, you can say, is a weight between bias of an input and A1. Fine. Let's see some other value. This theta 1, 1 multiplied with the x1. Fine. So this is, you can say, a weight between A1 and x1. Similar theta of 1, 2, where this 1 means A1 and this 2 means the x2. Fine. And whatever is that weight, we'll multiply it with the x2 itself. Fine. And so on. So now similarly, if you check the equation of A2 and A3, I hope now it's clear why we have 12 different weights, or you can say why we have 3 cross 4 or 4 cross 3 matrix for this theta 1. Fine. I hope it's clear now. And similarly for the next layer, the weight matrix, or you can say the theta 2, will be 1 cross 4, where 1 means the output layer and the 4 means the previous layer. 3 hidden and 1 bias. So is it clear? Fine. So likewise, for any kind of connection, you can calculate what should be the number of parameter, right? So this will refer this as a number of parameters, right? So right now for our network, for this very tiny network, can you tell me what will be the exact number of parameters that we need? The total parameter that we should have to complete the training of this neural network. Whenever I say total parameter, that means total number of theta values. How many different theta values that you need to store. 16, right? For the first layer, that is for the theta one, it's 12, and for the second layer, we have 4 more. Right? So in total, they are 16. So if you just consider this very tiny network where we just have 3 input and 1 output, still we need a 16 parameters, or you can say 16 features. We cannot say feature, but 16 weight values, right? And whenever we consider deep learning model, this 16 is just turn out to be 16 million or sometimes 16 billion. And so that is the only difference between this neural network, or you can say there is a basic difference between neural network and the deep learning model. We'll see in a neural network also, this 16 is a very small number, right? Whenever you consider actual neural network or whichever neural network that we'll design today, it also have more number of parameter than this 16. But this is just basic, right? But whenever we have that billion or million number of parameter, then it's an deep learning model along with some additional modification, right? But the basic structure is almost same, where we have the activation, where we have this kind of multiplication, or you can say linearity, and to avoid the linear, to add the non-linearity, we have the activation and so on. Fine. At that time also we are using the back propagation, the gradient descent, and so on. So almost similar concepts are there, but there are some slight difference. So we'll discuss it whenever we discuss the deep learning. Fine. And it is not always necessary that your number of layers are equal for all the layers except the output. So if you consider the second parameter, the second figure, where we have 3 layers in input, first hidden will have 3 you can say neurons. The second hidden layer have 2 neurons, and the output layer have a single neuron. Right. So can anyone quickly tell me what would be the number of parameter for this? And consider the bias term also. Total number of parameters. So we have different answers. 16 was the previous answer. 70, 20, 23. Any other? 23. 2 votes for 23. 3. And so you need to just consider number of parameters layer by layer. And if you consider layer 1 and layer 2, so how many parameters are needed? So four connections are over here, and we need to connect it with the 3. That will never give weight to the bias, right? So over here we have 4 neuron. In the next layer also we have the 4 neuron, but this x1's input will never provide to the bias. Fine. So the input is given to this 3 only. So 3, and this all will have 4 different inputs. So 3 cross 4. So once again 12 over here. Then layer 2 to 3. Similarly, you have to calculate that there are 4 input and there are 2 acceptors. So 4 into 2. And for the last layer, we'll have 3 input and only 1 acceptor. So 3. Fine. So finally, it's 23, right? Yes, I forgot to mention one point in the previous slide. So how will decide this number of hidden unit as well as number of hidden layers? It purely, and you can say trial and error, or it's purely an hyperparameter. But can you imagine how can we decide number of input as well as number of output that are not the hyperparameter? How many neurons are there in the input as well as how many neurons are there in the output? That two values are not the hyperparameter. That is fixed. So can you imagine what would be which parameter control that two values, or which factor control that two values? right? So at the first layer, let's say this x1, x2, x3 are nothing but our features. Fine. So we are assuming that we have an requirement, or you can say we have an application where we have three features. Fine. So that x value, or you can say layer one or the input layer, is always controlled by number of features. And so if I have 100 features, so in input we have 100 neurons, where each neuron is dedicated for, you can say, one particular feature, right? And that value will supply. Next, for the output layer, depends on how many output you want to produce. So let's say if it is a categorical data and we are supposed to have three category, so we'll have three neurons, and out of that one will activate, one will be activated. Fine. Or in general, you can say that last value, last layer will be number of classes. Fine. So with that understanding, whenever we have this multiple output unit, and consider this representation. So let's say we have four classes where we are supposed to represent, we have images, and from that images we are supposed to identify whether that image is of pedestrian, car, motorcycle, or it's of truck, right? So as we have four classes, we'll have four neuron in the output, right? And what we expect that 1000, 0100, 0010, or 0001 in the final output. So can anyone tell me what could be the best activation layer at the last output? That for the, you can have different try for middle layer as well as for the input layer. But can you imagine what could be the best activation layer for the final, that is the output layer? What would be the best activation function? Yes, wonderful. The final layer should have the softmax as a function. Why? Because softmax just gives you the probability distribution such that the total value will be 1. Fine. So actually in the output, you will have, instead of this 1000, what exactly you will get? Some probabilities for all four neurons. Right. And how can you convert that value into this 100 form? Once you have that probability values, thanks to softmax, how can you convert it into this particular form? Pick the highest probability value and consider it as a 1 and set remaining as 0. Yes, correct, Devang. Wherever there is a maximum probability, consider it as a 1 and set remaining to the 0. And that is, whenever you are setting something to 1, that means you are saying that this neural network has classified given image as that value. For example, let's say your output, if your output is 0100, where the second value is 1, which is representing a car. And so you can say the classification result is car, right? So this is what we are supposed to decide, right? Whenever we are implementing this neural network, what should be number of input, how we'll provide the input, and what should be the output, and how many output will be there, and how can we interpret the output, right? Otherwise, for the training and that all, once we use the sensor flow, they are just 2 or 3 steps, right? We already know that with the uh, logistic regression, we have tried this TensorFlow, right? So we know that the backpropagation, we are not supposed to do anything. Similarly, in today's lab, we'll focus on the TensorFlow. So we'll not do anything related to this backpropagation. So for this laboratory's perspective, I will not discuss anything related to the backpropagation. But yes, we need to understand the backpropagation. So in this lecture session, I will cover that backpropagation and the other learning. Okay, that's it. This knowledge is, I guess, not needed. And learning. Okay, so I will not go in the depth of this backpropagation, but let me just give you the intuition how this learning happened. So during the training, what happened? You have randomly initialize all the weights, right? So let's assume these are the weights. This delta 1, delta 2 are just the weight, right? So now, whenever sorry, that are not actually the weight. That are the error as per this particular calculation. Fine. So you have some weight at every layer, and due to that weight, there will be some prediction for a training set, and we know what is the correct prediction. Fine. So from the output, what we'll do, we'll go back towards all the units. So if you just go through this diagram, don't worry about the equation, just go through the diagram. From the output, we'll throw that error back to the previous layer. Both units of the previous layer. And from previous layer, once again, we'll throw it back to the its previous layer, and so on. We'll pass this value towards the first unit or the first neurons. Right? And we'll update the weight values. Right, so I'm skipping this particular part where the backpropagation concept is discussed in a little bit depth, but actually we'll discuss in more depth during the lecture session. And as it is not needed for the laboratory purpose, uh, we'll skip it. And let's start the lab task. Fine. So open the Colab notebook. So before starting any discussion, let's try to understand today's aim. Today we'll work on MNIST dataset once again. So can you recall what was the use of MNIST dataset? Or which kind of data? Yes. So basically they classify the numbers, right? And as an input, which kind of data we have? Right. So as an input, we have images in training as well as in testing. During the test, you need to identify which number is present in given image. Fine. And if you can recall more, this MNIST data says image size, if you consider a single example or the single input, can you recall what would be the image size? Right, so it was 28 cross 28, and right now in this example also is 28 cross 28, right? And it is also mentioned in this in one of the line. Fine. So we'll load that particular image, right? Or you can say we'll load images one by one. We'll train the neural network on the train set, and we'll try to predict the output of the test set, right? So that is the overall process that we were following since the first machine learning model we have designed, right? But we'll try the same thing now with respect to, or you can say with the help of this neural network. Fine. And to implement this, we'll use once again the TensorFlow. Fine. So can you imagine what would be the size of our input unit and what would be the size of our output unit? You can say input layer and the output layer. And whenever I say size, that means how many neurons will be there. So think about features and think about the classes. Excellent. So as an input, we'll have 784 units, or you can say 784 neurons. And in output, we'll have 10 neurons. Right, in between, we'll have some random number of neurons where that are the actually hyperparameter as we have discussed, right, for the hidden layer. Where the 784 is nothing but the 28 cross 28, or you can say all pixels from particular image. Fine. So we'll consider a single image that is of 28 cross 28, and we'll consider all pixels of that image as one feature. Fine. So starting from the first pixel up to the last pixel, all are a individual feature. Fine. So this is the simplest representation of any image. We'll consider all that particular pixel as an image. Fine. And in output, we know that the size of output against the number of neurons in the output layer should be equals to the number of classes, or you can say number of values that you want to produce. And we know that this MNIST is the digit data set where we have all the digits starting from 0 up to the 9. So we have total 10 classes, right? So with this basic concepts, let's begin. So the first cell, just run the first cell where we are supposed to import a particular libraries, matplotlib, numpy, pandas, as well as torch. And from the torch, we'll use the neural network, right? So we'll use a particular linear layer from this neural network, right? So let's include it. And what is the use of this variable, if you can recall? I guess from this you can recall autograde. Right. So to automatically calculate that gradient descent, we are supposed to, whichever parameter that we want to update automatically, we have to save it as a variable rather than considering it as a tensor. Right. So we'll update our weight and the bias as a variable so that it can be tuned, or you can say it can be changed by a model during the automatic backpropagation process. Right. So that's why we'll use this variable. The data loader, just to provide the data, and I guess uh, none of you have the doubt in this train test split, right? And in today's lab also we'll follow the same practice there where the random state is equals to your roll number, right? And so we'll just use this train test split to divide the training as well as the test data set from the given input, right? Next, in the next cell, we'll import the MNIST from this TensorFlow Keras data set, right? Now let's begin the code. So okay, you can refer or you can open that particular slide, that that particular notebook where we have designed this MNIST, where we have used this MNIST data set as well as where we have used this TensorFlow, right? So to recall some of the syntax, that particular notebook might be helpful. So I advise you to open that notebook if it is available to you. And so I'm giving you 2 to 3 minutes and just try to open that two notebook, one where we have used this MNIST dataset, another one where we have used the TensorFlow. Okay, so to load this MNIST dataset, so we have this images as an input, and we have this feature train, target train, feature test, and the target test. Right, so that means the train set as well as the test set ready. So you can print any of the image, maybe from the feature or maybe from the training or from the test set. Next, we are converting it to the float. Then, as we have discussed, this number of feature will be 784, which is nothing but the 28 cross 28. Next, reshape your train as well as test images. And what will be the new dimension? So right now it is 28 cross 28, that is a square matrix. But if you can recall one of the laboratory where we have handled the image, what generally we'll do with the images? Right, we'll flatten that image out. That means we'll have that all the row, let's say if we have 28 row and 28 column, so let's assume that we'll consider the first row, that is first 28 pixel, followed by the second row, followed by the third row, and so on. And likewise we'll arrange it into one single row, and so on, will create a one single strip of a particular example. Fine. And how many such examples, that we don't know, but one good thing with this reshape is, let me just write the syntax. So first, feature trend dot reshape. So this is for the train, and similarly we need to repeat the same process for the test. So can anyone tell me what would be the reason of this -1, or what is the use of -1 whenever you use it with this reshape? If you observe, the reshape dimension is -1 cross, you can say, number of feature, and we know that number of feature is 784. Right, so this indicates 784. But instead of writing 1, why I have written this -1? Yes, correct, Anshuman. Because we don't know how many rows are there, right? This 1 cross 784 is just for single examples, a single example. But whenever you're not sure that how many rows are there, what you can do, you can put -1 over there. So it will calculate accordingly. Whichever number of rows are there, it will put that value over there. Right? And this is purely valid for, yes, -1. That means it will figure it out. It is equally valid whenever you have n number of dimension. Right now we just have two dimension, right? Number of row cross number of column. But let's say if you have n number of dimension, any of the dimension, if you are not sure that what should be the value, then you can put that -1. Right? So let's say I don't know the number of column, but I know the number of rows. So you can specify the row value, and the column should be -1, and it will calculate it by its own. Fine. So we have reshaped these particular features. Then we'll normalize that particular value, because if you consider the images, the values are between 0 to 255. That all the pixel values are between 0 to 255. We already have the float data, so we'll convert it into the float value by dividing it with respect to 255. And so all the values are now between 0 to 1. And that's why we have that float conversion. Right? Next, these features are just in NumPy array. You need to convert it into the tensor. So can you recall which function we can use? હવે તો કહો. Yes, correct. From NumPy. And the size of the target will be converted to the long value. And similarly, you have to apply the same operation on the test, right? So feature test as well as the target test. So complete this step: feature test as well as the target test, convert it into the tensor from this NumPy. Next, we are setting some hyperparameter, that is what should be the base size, as we are going to use stochastic gradient descent, and the number of iteration. For the number of epoch, this equation is very popular, but otherwise you can just take it, you can consider it as in some hyperparameter. You can just consider it some random value, right? And we'll bundle it together using this tensor data set. So feature train, target train, which is ultimately the train. Fine. And similar, the bundle of this feature test and the target test will be your test, right? And we'll feed it to the data loader by setting bed size is equals to this particular bed size, and let's say the shuffling is false, right? So we have discussed this in the past laboratory, what exactly the use of the shuffling as well as the bed size. Can you recall what was, I guess shuffling is shuffling might be clear, but can you recall why we are passing this bed size over here? Right, and let me just run this particular cell. So meanwhile, once you observe the output, think about the okay, so we have some error over here. So can you figure out what exactly the reason for this error? Targets. Okay, so right, so we have just printed some random image. You can choose some other image and you can try to print that image, and it represent the number which is stored inside that particular image. Okay, so why we are passing this bed size over here in this data loader? And now onwards in the artificial neural network design, we will use this train loader and the test loader. So if you consider the gradient updation, or you consider the weight updation, so what do you think during the training? Let's say if we have 1,000 examples, so for each example we'll repeat the process, that is we'll pass that image from all the layers and we'll observe the output, and if there are some error we'll go back towards the first layer and we'll update the parameter or update the weight. We'll repeat this process for all 1,000 image, or you can say all 10,000 image. So the first answer is yes, we can, right? But can you find any limitation of that? If I repeat this process for all the examples, it will be bit slower. Right? The training process may take more time because for all the examples you are updating all the weights. So rather than that, another variant of this gradient descent, which is referred as a batch gradient descent, where we'll deal with the batch. And as Zainam has mentioned, rather than doing it for a single example, let's do it for a batch. So we'll have for this particular example, what's our batch size? That is 100. Fine. So we'll do not update any parameter for first 100 examples. Right? We'll just keep a note of that this particular image is wrongly classified, this is wrongly classified, and so on. And once the first 100 iteration, when the first 100 image are already processed, then we'll go back, and or you can say then we'll apply the back propagation, or you can say then we'll go towards the backward pass. Fine. So the first approach is totally valid. Remember that for an individual image, you can always follow the forward pass and the backward pass. There is no issue in that. No technical issue in that. The only problem with that approach is it is little bit slower as you are updating the weight for individual images, right? So if your input size, or you can say your total number of inputs are very large, then it is the training will take more time. Fine. So rather than that, mostly or majorly people are following this approach, that is the best version of the gradient descent, where instead of updating for every image, or you can say for every example, we'll collect some example, and that example, the collection is referred as a batch, and batch by batch will process the given input. Right, so that's why we are passing this batch size into this data loader. And so that's why whenever we iterate or whenever we enumerate from this data loader, we'll get one by one batch. And if you can recall, this train just contains all examples of your training, but we need batch for processing. Right, so that's why we are using this particular batched version of gradient descent, and that is also referred as stochastic gradient descent, SGD. Yeah, the concept is simple. In the batch processing, what we are doing, we are not updating the weights. So if you just consider the logistic regression, forget about the neural network. What we were doing, we'll pass an example, we'll observe the output, we'll update the, we'll check the error, we'll update the parameter, and this will repeat for all the examples of a training set. Fine. So that is fine unless and until you have a single neuron, right? So you can that logistic regression is actually one single neuron. But now we are dealing with the neural network where we have many neurons. So if you repeat the same exercise for all the neurons, so assume that in the model that you are going to design that have 100 neurons, right? You have designed such that there are 100 neurons. So for 100 neurons, if you repeat this process, that is, I will pass one image in a forward pass up to the end, we'll observe the error at the end layer, or you can say at the output layer, we'll update the weight of output layer, and we'll pass that updation towards the previous hidden layer. Once again, we'll update the weight, we'll pass that updation to the previous hidden layer, and so on. When we'll follow this exercise till input. Fine. So if you follow this practice for all individual image, your processing will bit slower. Rather than that, the concept of batch is very simple, where forward pass is anyhow needed, right? So we'll pass all the images one by one, and we'll observe the output. This output is correct, this image is correctly classified, this is not classified, correctly classified, not classified, and so on. Let's say batch size in our example is 100. So once the process of first 100 images is over, till then we'll never worry about the back propagation, or you can say we'll never think about the backward pass. At the end of 100th image, we'll update the weight according to all that 100 images, right? And we'll pass that weight backward towards the first layer, right? So that is just, you can say, combining the weight and the combining the error and then lateral passing that error towards the first layers. Fine. So instead of repeating it for 100 times, I will repeat it for one time only for the batch of 100. So if I have such 1000 images in a training, so I'm supposed to use back propagation for 10 times only, where previously we are supposed to do that updation for 1000 times. And so that is the batched version of the gradient descent. Is it clear, Vivek? Okay. So this, if I focus on this line, the train and test, which contain the tensors for all the training and the test example, right? But whenever we enumerate, we'll enumerate on this data loader. So in a data loader, we'll pass, or you can say we'll feed this training and the testing along with the batch size. So whenever I request for the new input, we'll have that batch accessed. Fine. And now the next cell is very much interesting, or you can say very important. So for this artificial neural network, we are creating a class, and the name of that class is, let's say, ANN model, fine, where the input is nn.model. And now what is this nn? Just check your library and tell me what's the meaning, what is the role of this nn, what exactly this nn is. In the first or the second cell, I guess we have defined that nn. So just check that first or the second cell. Right. So that is the neural network that are available, or you can say the layers of neural network that are already available in this torch. Fine. So okay. So I guess before seeing this particular cell, let's see the next cell where we have input to this neural network. And just focus on this line. We'll call a model with train. So what is the train? That is actually the image that we have. Fine. And from where we are supposed to retrieve that image? From the train loader. Right. And what is this train loader? Can you just check the previous cells, and can you identify where this train loader is? Right. So that's an data loader, right? Okay. So this understanding is needed before discussing the model, the designing of model. So now let's go back to the previous cell. So in this init, we need to design the layers, right? So that designing is totally up to you. You have to be restricted for input and the output, but except that you are free to choose number of number of hidden dimension as well as number of hidden layers also, right? So let's say at the first we'll have 150 hidden layers. So the first linear layer that we are going to inherit from this nn will have input dimension What is the size of that input dimension? Have you mentioned it above or it's below? Okay, so it is mentioned over here. Fine. So just note this down. Input dimension, that is you can say our image size. Hidden dimension 150. Output dimension. What will be the output dimension? 10. Right. So let's keep this thing in your mind. Input, that is 784. Then the hidden. We have fixed this to 150. Right. You can update that value if you need. And the output is 10. Fine. So let's see the designing of this particular neural network, which is very easy with thanks to this TensorFlow version. The first is you need to design the computation, that is a linear layer. What should be the dimension of that linear layer? So it is input cross, you can say hidden, where the input is 784 and the hidden is 150. Fine. So that will be our first layer. Right now we are just creating a layers. Remember that we are not making any connection, right? Which layer will be connected with which, and that we are not making. Right now we are just creating layers. Right? Next is the activation for the first layer. Let's say we are using the ReLU for that. Have I discussed that ReLU in any of the laboratory or maybe in any lecture? Yes or no? No. Okay, so I need to spend some time on that. There is a very popular activation function which is used with many neural network as well as many deep, specifically with the deep neural network. So if you are referring some of the website related to deep neural network, you must have heard this particular word ReLU, right? Due to its simplicity. So if you just refer this figure in the real ReLU, what happened for the positive value, that is the value which is higher than 0, it keep that value as it is, and for the negative value it just clip it to 0. Fine. So can you tell me what will be the implementation of this ReLU? If you want to manually design this ReLU function, what should be your code? Let's say if x is less than 0, the output is 0. Rather than x, you can say y is equals to 0 or return 0. Yes. So, and otherwise, return x as it is. Right. So simple, this calculation is there. Now think about the sigmoid activation, where you have to calculate 1 upon 1 plus e raised to something something, right? And where we just provide that something something, but that 1 upon 1 plus that computation we are supposed to do, we means the that computation is needed from your machine, right? And remember that this computation we are repeating for all the neurons of a particular layer. Fine. So that activation, if you use the ReLU as an activation, the computation of your activation is very 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 fast compared to the other function like sigmoid or 10h and so on. Fine. And there are many variants of this ReLU. If I can show you one variant, the leaky ReLU. I guess that figure might not be visible, so let me have some larger figure. Uh, yes, this might be visible. So can you observe what is the difference between that ReLU and the leaky ReLU? The first is the ReLU function, and another one is the leaky ReLU function. And I guess from the name also you can identify what exactly the difference. So in the case of this leaky ReLU, for positive, the working is as it is. We'll just have whatever is input that will produce as an output. But for the negative, rather than keeping all the negative value to zero, or rather than clipping all the negative value, we'll keep proportion, some portion of that particular negative value. Not the exact answer, but some portion of that level. So you can say in a negative direction that ReLU function is leaking. So that's why the name is leaky ReLU. So there is some leakage in the negative portion rather than keeping it to the zero. There is some minor leakage. So that's why it's a leaky ReLU. Once again, you can control how much leakage you want. And so that is the another version of this, another variant of this ReLU. And so, but this is one of the activation, very popular activation function with the deep neural network, where already we have very large computation. So to avoid this unnecessary computation of additional unnecessary computation of activation, this ReLU is very much popular. Fine. So we are fixing the second layer, that is the ReLU. Right. So now your role is to fill these remaining layers. And remember that we are just creating the layer. There are no connections. So we just have the layers FC1, ReLU1, FC2, 10H2, FC3, ReLU3, and FC4. Fine. So just try to create the remaining layer. The dimension are already mentioned, so that might be helpful to you. So just try to complete these remaining layers. And as we have already discussed, this particular final dimension will be 10. Then there is one another activation function. You can also use that. That is ELU. Or if you want, you can also stick to the ReLU. Fine, it doesn't matter. So done. Have you completed this part? Okay, fine. So we have just designed the layers, right? So there are no connection between the layers. So next, let's define another function, that is forward, which is actually indication of the forward pass, where we'll actually have a connection between these layers. Fine. So in a forward pass, we'll pass the X, where X means your input. So to which layer will provide our input? So all the layers are ready. Now just connections are remaining, right? So to FC1, we are supposed to provide this input. So let's say self dot FC1, and the input to that FC1 would be X. And let's say the output produced by that epsilon will be out. Now next what? Activation of layer 1, right? So for the activation of layer 1, so what is the name of that activation of layer 1? What is the name of activation of layer 1? Yes, relu1, right? The function name is relu, but the over here we have created the variable that is relu1. Fine. So self relu1 would be the input. Yes, the output from the first linear layer. Right. And let's say the output produced by this first non-linearity, or you can say output produced by this first activation. Once again, we'll name it as an out. And so I hope now you can complete the remaining portion of this forward pass. And so just complete the remaining portion of the forward pass, and then once again we'll continue with the discussion. So I'm giving you some time, just complete this particular code. Okay, so this part is ready. Input dimension that you already mentioned, hidden dimension, output dimension, and the model, that is ANN model, that is we are going to call the particular function with input, hidden, and the output dimension. Fine. So this class, the ANN model will be called with that input. Fine. And as in loss, we'll use this cross entropy loss. What do you mean by cross entropy loss? Once again, for that the function is available in this, right? So no need to redesign that function. So can you recall what was the meaning of cross entropy loss? Haven't we discussed this cross entropy in the past? Right. And for this STD optimizer that we are going to use, the learning rate that we are setting to 0.02, right? And once again, this optimizer is available in the torch. So torch.optimizer, that is optim, and which optimizer that you want to use. So we are going to use this STD. Fine, and the parameter will be the models parameter, and the learning rate will be the learning rate that we have just set, right? And if you can recall, this learning rate is one of the hyperparameter since we were learning the first model, right? And so, are we clear with this cell? Any doubt in this particular cell, the creating ANN model? So, okay, so right now there are no error. So, any doubt in this particular cell? Should we move ahead? Right, so our model is ready. Now let's start with the training and the testing phase. So we have some list to print the actual output. So what we'll do, we'll use a strategy to store the error as well as you can say the accuracy after some iteration. Will not trace it after all the iteration, right? Unnecessary will not do that processing. I guess we have done the similar practice in one of the laboratory in past too. And so let's say maybe after 50 or 100 iteration, we'll check what is the error value, what is the loss value, and whatever that value that we'll try to plot with the help of graph. Fine. So that's why we have this empty list. So now in this for loop, for all the epochs, and this number of epochs we already mentioned, right? So that is one of the hyperparameter. From this train loader, we'll have image and label. And if you can recall in the loader, whenever we have created that data loader, at that time we have merged it together, image as well as the label. And so we'll keep image and the label in a variable, right? And the name would be train and the label. Right? And I hope you can recall now. You can recall what is the meaning of this -1, 28 cross 28. Right? Once again, the meaning is same. And so for resizing, that would be -1 cross 20, -1 comma 28 cross 28. Fine. So now you need to refer the Python file that we have created in one of the laboratory, and you need to refer the steps of this gradient. First, you need to create that. First you need to clear that. So if you can anyone recall the function? Now from this, can you recall the function? Our optimizer is stochastic gradient descent, right? So now from this particular list, can you recall how can we clear this gradient? આમાંથી કંઈક જાણીતું લાગે છે? Yes, zero grade, right? And output will be model and the train that you are supposed to supply, right? And as we know that it's a classification problem, and as we have just referred in the slide, the next would be the whatever is the output produced by the model, we are supposed to apply the softmax, right? And for that the error would be the cross entropy loss. And so let's say the loss would be the error, that is the cross entropy loss with output, and the original output is labels. So the first value output is your prediction, and this label is the correct output. Fine, and based on that, we'll apply, we'll calculate this cross entropy loss, and whatever is the result, that is the loss value. Next, with the help of loss, we'll use the back propagation, right? So that is, we'll calculate the gradients. So this loss dot backward, right? Next updation. Okay. Last option. Yes. Now this step. Akshay, what you're asking? Last option is it a question or? And so this is updation. That's it. And we know in one of the laboratory we have tried the same thing, right? We have first clear the gradient, train the model, calculated the loss, have this backward, and at the end the updation. So that would be the calculating the gradient, and at the end the updation. So that is the step. Fine. So that's it from the processing perspective, or you can say from the trainings perspective. But now to print the output, or you can say to print the error graph, or you can say print the accuracy graph, what we'll do, we'll try to trace number of iterations. Right. So that is one counter. And whenever counter modulo 50, so after every 50 iteration, we'll calculate this fundamental. So that's why we have that list. Right. So let's see what we are doing over here. So for image as well as the label that we have right now, we'll recalculate the answer and we'll have the prediction from the maximum, right? If you can recall, if you can recall that particular slide where we have that pedestrian, then car, bus, and that image. At that time, we have discussed that what we'll do, we'll find the maximum. I guess Devang has answered that, right? So whichever is the maximum, that would be, you can say, your prediction. And then we'll calculate that correct value, and based on that, we'll find the accuracy. Fine. And whatever is the loss value, that will store into the list that we have just created initially, right? So that empty list, in that we are appending the loss as well as the count and the accuracy value. Fine. So lateral we will use this particular list for designing a graph. Fine. And let's print this loss value after every 500 iteration. You can also print it after 50 iteration, right? It doesn't matter. So let's see if everything is fine, then it should give the output, right? But there is no name output. So it's outputs. સાથે જો બધા મોડલ ફરે છે. Fine. And the last thing is just the visualization. where from the list that we have just generated, we'll just try to plot it using this matplotlib plot function from the matplotlib. So we'll try to visualize loss as well as the accuracy, or we'll try to plot loss as well as the accuracy in two separate graphs. And then some labels that you have mentioned, X label will be that number of iteration, Y will be the loss, and just the title for the particular image. And so if you observe the loss as well as the accuracy value in terms of graph, so this will be the result. So now you have to try the same model, or you can say same approach, that is ANN, on the fruit data set. And the link of the data set from this Kaggle website is given over here. But if you do not have the that much data, because I guess the data size is around 720 MB, and so if you do not have the data, or let's say if you are restricted to half GB per day, then you can have your own data set. So in such scenario, what you can do, you can download 20 image of one particular fruit, let's say 20 image of apple and 20 image of orange, fine. And on that you are supposed to train the model, and you are supposed to predict the performance. But if you really have the connection, then you must go with this particular large data set, which gives you the real touch. And I'm not restricting you guys to have number of hidden layers, the number of data, or you can say number of input in the hidden layer. So it's your choice how many hidden layer you want, as well as what should be the number of neurons in that hidden layer. So that's totally up to you, right? But I'm restricting you with only one thing, and that is this random state, right? So the random state value must equals to your roll number, and whenever you submit this particular laboratory, it should be equals to your roll number. Other thing that I encourage you to fully try, so you are totally free to try different variants, right? And also I encourage you to try 2 or 3 model, and you can also compare the performance of the 2 or 3 model, right? So let's say in one model you have 3 hidden layer, and the second model you have 5 hidden layer. Also you can vary the number of neurons in the hidden layer, and you can also observe the performance of that 4 to 5 models that you have designed, right? And if you are really doing that stuff, then also include it into the submission, right? So I came to know that you have done all that stuff, though it is not essential thing is you need to just use any of the approach, either the fruit data set from this Kaggle website, or your own created data set where you have 20 image of one fruit and another 20 image of other fruit, and make sure that you use the fruit which looks bit similar. For example, let's say apple and orange. I don't have one fruit as an apple, another fruit, let's say grapes or the banana, right? So where anyone can easily able to identify what exactly the difference. And so let's have bit difficult data set by providing this kind of fruit. If you do not have the data, right, but if you have the data, you must go with this Kaggle set, right? So I will not verify your performance on that parameter, whether you consider this Kaggle dataset or your own dataset, right? So it might possible that some of you may not have that much data available, right? But yes, this random state, as well as how much processing that you have done, whether you have created 2 3 model and whether you compared the 2 3 model or not, based on that the performance of this lab is evaluated. And one more thing that I want to discuss is for the next laboratory, that is on this Sunday. Uh, what do you expect? Do we should we discuss the CNN, or should we discuss the SVM? CNN to what? આમાં તો જેટલા 62 પ્રેઝન્ટ છે બધા કહી શકે, કાઢી નાખો 60 જેટલા પ્રેઝન્ટ છે બધા કહી શકે આમાં તો. Once again, I'm observing how many of you are actually attending the lab and how many of you have just started the session and just joined the session. Fine, so we'll go with this CNN as the majority what is there, but we'll also cover this SVM, right? So Kashyap, I guess Kashyap એક જ કીધું છે SVM કે બીજા કોઈ કીધું છે? We have some additional laboratory, so anyhow we'll cover that SVM. So maybe let's say SVM might not completely discuss theoretically in the next session, so let's but probably it will be discussed, but fine, we'll discuss this CNN in the next laboratory, and in next laboratory, that is in next week, we'll discuss the SVM. Fine, and if the PCA is covered, then we'll discuss the PCA also. Otherwise, we'll see whether we can cover LSTM in the laboratory or maybe some other model, right? So if I guess we can cover this CNN as well as the LSTM, similar to the current lab where we have some basic intuition first and then the implementation of that CNN, the basic CNN, the basic LSTM, then you have knowledge of both current, I can say it's current, but recent deep learning models, right? So even those who are interested in the NLP and those who have studied these models, some RNN based model, maybe the LSTM, then for them the one news, or you might aware about that news, that the encoded recorder based architecture or the attention based mechanism is right now very much popular, and such that now people are moving from that RNN based model, that is from the LSTM, they are moving towards something referred as a transformer, which is once again the attention based mechanism where there is no recurrent network or there is no recurrent connection. And very popular models on this transformer are the BERT model, which is given by Google in 2018, and the GPT models. There are many variants of this GPT model. The recent one is GPT-3, which is given by the OpenAI, and I guess it is in this 2020 itself. So that are the model where people are moving, or that are the transformer model where people are moving from this deep learning based deep learning based RNN model, that is recurrent neural network model, of this text processing, or you can say the NLP processing, right? So we'll I guess we can't able to cover that transformer, we do not have time for that, but we'll surely try to cover that at least up to LSTM, and similarly for the image processing perspective, the CNN model of this deep learning. Fine. So maybe in my lecture as well as in the laboratory also, and also there is sometime then in SARS lecture 2, we'll have discussion of that models, and surely we'll try to implement one or two of them in the laboratory. I'm not sure about that transformer based model, but you can refer the transformer based model maybe in towards data science or DM or some other good websites. So look at the model like BERT or GPT, and if you are interested, and then you may find some application of that models too. Fine. So with this, let's conclude this session, and in the next session, what we will do, once again, we'll pick this MNIST data set, and for this with this MNIST data set, we'll have the CNN model, and maybe this file itself will come will combine the CNN model so that you may observe some important difference between the CNN and this basic neural network, which is machine learning based approach. The difference that we are interested to learn is in terms of accuracy, second in terms of speed. And so that two difference you can easily observe once we compare the two models. Right. So let's conclude this session. Have a nice day.